Hey everyone, so today what we're going to go over is the unit circle, and specifically how to gain a little bit more understanding and intuition of it, just to make it easier to remember. This is at least the way that I best remember the unit circle, so I hope it helps you out. Because when we see stuff in like our trig class about these triangles in which you have a 30-degree angle, you have a 45-degree angle, and you have like 60-degree angles, we may sometimes ask why these angles specifically. Like, why do I just need to remember these ones? How come, like, why not 10 degrees? How come 15? 45 may be a little bit easier to understand because, okay, well, if you have a 0 degree and a 90-degree angle, then it's like the in between of them. But then why these 30 and 60 angles? It's just weird. It's just weird. And so hopefully with this video, you gain some understanding of where those angles are coming from and have a better way of remembering the unit circle. So before we talk about the unit circle, we need to talk about just circles specifically. And so how do we define a circle? So a circle, draw this big circle here, is defined by a curve in which each point on this curve, all these points that I drew in red, they are what we say is equidistant or equidistant from some center point. And so what that means is that all these points on the curve here, they all have the same distance from this center point, in which this center point here we can call the center of the circle, and this distance from the center of the circle to the edge of the circle we call the radius of r. And now how do we create an equation from this that describes this circle? And so from this here, what you'd actually be able to see is that, let me get rid of some of these lines just to make it a bit more clear, is that if we have this distance from the center to the edge of r, we'd actually be able to draw a triangle here in which you have the distance of one leg of x and the distance of another leg, specifically the height, of y. And so what that gives us is a triangle of hypotenuse r, length x, and length y. And so what we can do from here is use Pythagorean's theorem, in which if you want to think this as a, b, and c, you know that a squared plus b squared is equal to c squared. And specifically for this triangle that's describing our circle, we have x squared plus y squared is equal to r squared, where the special property here is that this r value is a constant. It is not changing, but our x and y values, they can change in order to give us different xy pairs to give us a point on this graph. Just label my axes there. And we can have different points around here in which give us the same r value. And so now the jump from circles to unit circles is quite simple, in which if we want to specifically talk units, we want to make stuff easy on ourselves. We want to think in values of 1. And so from our value of, from our function of x squared plus y squared is equal to r squared, what we can say is, okay, well, let's just make that constant value of r, let's just make it a 1. Let's just say r is equal to 1. If that's the case, then x squared plus y squared is equal to 1 squared. And we all know that 1 squared is just equal to 1. And so now we have this equation that's a little bit simpler to think about. X squared plus y squared is equal to 1. And so what I'm going to do here is I'm going to draw a smaller circle, draw my axes through here, in which the center of the circle I'm going to set as the origin, 0, 0. And then the radius of this circle is 1. So with this, there are a few points in which we'd be able to determine right away, knowing that the radius of the circle is 1. The simple ones would be the points on the x and y axis, right here, which would be 1 step to the right and 0 steps up, which would be 1, 0. 1 y-intercept here, which you go 0 in the x plus 1 in the y. Another x intercept here, in which you're going negative 1 in the x, 0 in the y. And the second y-intercept here, in which you're going negative 1 in the y. Mixed my axes up. That happens sometimes. When you're going 0 in the x and negative 1 in the y. And so now with this, what we're specifically saying here is, okay, well, if I plug in 1, say for instance, right here, 1 and 0 into here, if x is equal to 1 and y is equal to 0, we have 1 squared plus 0 squared is equal to 1. 1 plus 0 is equal to 1. And yes, we know that that's true because 1 is equal to 1. But what are some other values in which we know? Well, it might be hard. I'm going to go ahead and erase this example here. It might be hard if we consider the entire x squared term, or I should say specifically if we consider just x and just y, and considering the squaring of those terms. It might be hard to think about what values of x and y make this equation true. But if we just look at x squared as a whole and y squared as a whole, then we'd be able to find a couple of values in which can be relatively easy for us to determine, in which we say, okay, well, let's say if x squared is a fourth, let's say it's a quarter, and in that case, y squared, if we want to sum these and add them up to 1, then y squared must be 3 quarters, right? If you have a quarter and then you have add 3 more quarters, then that'll get you up to 1. And so now looking at other values, we can see that we'd be able to also use x squared is equal to 1/2. Y squared is equal to 1/2. We can also use x squared is equal to 3/4, and y squared is equal to 1/4. All these together, if you add up x squared plus y squared, they're gonna equal 1. And these are specifically just like easier values on the first quadrant, in which for these 1/2 here, if you want, you can also think of this as x squared is equal to 2/4, and y squared is equal to 2/4. It makes it easier to go from 1/4 to 2/4 to 3/4. And in y squared, you're going from 3/4 to 2/4 to 1/4. In fact, you know what? I'm just going to write this here. It is a nicer pattern to think about. And so we can say that this is 2/4, a half. This is also 2/4, a half. And so with these values, we can just look at the first quadrant here. So I'm simplifying this unit circle right here just to the first quadrant, in which you have 0, 1 right here, and you have 1, 0 right here. And so for our 3 values of 30, 45, and 60 degrees, we'd be able to see that, okay, well, if we're traveling more in the x, a little bit up in the y. That this point right here would have to be, if we're thinking about these in terms of x squared right here would be 3/4, and y squared right here would be 1/4. Right over here would be x squared is equal to 2/4, and we would have y squared is equal to 2/4 as well. This value right here would be x squared is equal to 1/4, because we're traveling only a little bit in the x, traveling more in the y. So y squared would be 3/4. And so we can see, well, for these 1s and 0s here, these are in terms of x and y, but for these 3 new points, these are in terms of x squared. And so all we're going to need to do is just square root on both sides of these equations here. So square root, square root, square root, square root. And what that's going to actually give us is, I can wipe this out. I'll do this step by step. So this is square root. This was a fourth here, and this was square root of 3/4. In which then now the square root of a fraction, you do the square root of the numerator, and then the square root of the denominator separately. So square root of 1 is just 1, and then square root of 4th is 2. So this will be 1/2. For over here, we do the same thing, in which we do the square root of 3 over the square root of 4, and be the square root of 3/2. Right here, square root of 3/2. And so now I'm going to do the same exact thing for all of these fractions that we have here. So this was the square root of 2/4 and the square root of 2/4. So these will both be the square root of 2/2. Square root of 2/2. This point right here is just what the first example that we did, except the x and y values are flipped. So this is square root of 3/2 and 1/2. And so now with this, we've been able to derive the points in our unit circle from just knowing what a circle is and knowing Pythagorean's theorem. But it still begs the question, well, okay, what about these other points and these other quadrants? And also, what about these angles? You just kind of put these angles, but why are they still just 30, 45, and 60? Let's first answer that second question. And then the answering to the first question will be kind of like the generalized summary of all this. So if we grab any of these values here, let's grab this first one of the x squared is equal to 1/4 and the y squared is equal to 3/4. What that would give us is this triangle in which you have 1 for your radius, right? In your x direction, over here, in your x, it's your y. In your x, you said that that x squared specifically is 1/4, and y squared was 3/4. And so if you want to think about this in terms of a, b, and c, I guess for this I'll put our radius is equal to r. Again, this is our c is equal to 1. Our a is equal to, this would have to be the square root of 1/4. And our b is equal to the square root of 3/4 here. Whoops, that looks like a 9. The square root of 3/4 here. And so you can think about this in terms of the a, b's, and c's. or the x, y's, and r's, which you can say x squared plus y squared is equal to r squared, or you can say a squared plus b squared is equal to c squared. In terms of this example, we'll use the x squared plus y squared is equal to r squared, in which we know that x squared is a fourth, y squared is equal to 3/4, and r is equal to 1. But now with this, we need to calculate the angle of this triangle, specifically right here, because if this point right here is our origin, the point 0, 0, then we have to see, okay, well, if we use our SOHCAHTOA, then we know that we'd be able to say that the tangent of this angle is equal to the opposite, in which in this case it'd be actually, yeah, I guess we should use the a's and b's for this, because then what I'm going to say is it's equal to the side, the length of the opposite, in which if we're at this angle right here, the opposite is directly across, in which it would be b. And then, yeah, this will be b over the adjacent, which for this angle would be this leg right here, in which in this case this will be a. B over a. So let me actually just change this. And what did we say? We said that a is equal to square root of a fourth, b is equal to square root of 3/4. And so tangent of theta would be square root of 3/4 over square root of 1/4. And now if we just spend some time with a little bit of algebra here, we can say that this is the square root of 3 over the square root of 4 divided by the square root of 1 over the square root of 4. We have division of fractions, and so we're going to do a keep, a change to a multiplication, and a flip to square root of 4 over square root of 1. And you'll be able to see that the square root of 4's cancel out here, and you have to put the square root of 1 on the bottom here. And this would be square root of 3 over square root of 1, in which square root of 1 is just 1. And so you're left with this equaling square root of 3. And so now you have tangent of theta is equaling square root of 3. And now if you want to calculate the angle specifically, you'd say that theta is equal to the arctangent, because what we're actually doing is on both sides, we're doing the arctangent. And if you just have the arctangent of the tangent of theta, these two are inverses of each other, and you just left with theta. And now you have the arctangent of square root of 3, in which you would need to do some tricky math in terms of just this video. You'd be able to use a calculator, in which then you would get a form of radians, in which then we can convert into degrees. And then you should find that this theta is actually it is 30 degrees. And we'd be able to do this same process for every single part of the triangle. And then as for the other parts of the triangle, we'd be able to use symmetry. And then if we do a symmetry from one side across the x-axis, then we can grab this whole half circle and then flip it across the x-axis to get our whole circle. And so once we figure out one quadrant, then we figure out the entire circle by symmetry. But for now, we just worked with the first quadrant. And now to summarize all this, because I may have lost you with figuring out the degree. Don't worry about the degree. You don't have to, because now this is the generalized method in which I used. So, drawing out the unit circle, all you need to know are the 4 points, the 4 easiest points of the unit circle. And if you don't know them, you can just draw out a graph, and just know that the unit circle is always just a radius of 1. And so that means this point must be 1 in the x, 0 in the y. This must be 0 in the x, 1 in the y, -1 in the x, 0 in the y, and then 0 in the x, -1 in the y. And now what are we going to do? We know that we have 3 points along here on each of these quadrants. And so what I'm going to actually do is I'm going to first focus on the x value. And notice that I'm going from 1 to 0 to -1 to 0 and back to 1. There's not really a jump. We're always just changing these values by some factor of 1, where we're going from 1 to 0, that's -1, 0 to -1, that's -1, -1 to 0, that's +1, and then 0 from 1, which is +1 again. And if I need to do these steps in between, I'm just going to go by factors of, or by quarters. And so from 1, I'm going to subtract 1, which is 3/4. My bad. Subtract the quarter, which is 3/4. Subtract another quarter, 2/4. Subtract another quarter, 1/4. Subtract another quarter, that gets you to 0. Keep following that pattern in which, okay, now I'm going from 0 to -1. So I'm going to keep decreasing. So now from 0 minus a quarter, I'm going to go -1/4, minus another quarter, -2/4, minus another quarter, -3/4, minus another quarter, that gives you the -1 over 0. Now I'm going from -1 to 0, in which now I'm increasing by 1, and so now I need to start adding on quarters onto here. And so this is going to be -1, I'm going to add a quarter, now it's -3/4, add another quarter, -2/4, add another quarter, -1/4, and then I'm at 0. And now I'm at 0, I'm going from 0 to 1, in which then I'm going to go from 0, add a quarter, to 1/4. From 1/4, I'm going to add a quarter, 2/4. And I'm going to add one more quarter from 2/4 into 3/4. And that gives me the 1. And so now this cycle is complete, in which from each point, from point to point, I'm going just by either adding a quarter or subtracting a quarter. And I'm going to do the same exact thing for the y values. So I'm going to do this quickly. 0 to 1, I'm going to be adding 1. And so I need to go from 0, add a quarter, 4th, add a quarter, 2/4, add a quarter, 3/4, add a quarter, that's at 1. We're going from 1 here to 0 here, which means I subtracted 1. Subtract a quarter, that gives me from 1 to 3/4. Subtract a quarter, down to 2/4. Subtract a quarter, down to 1/4. Subtract a quarter, I'm at 0. From 0, I'm going to -1. So now, from 0, I'm going to subtract a quarter, in which that gives me the -1/4. Subtract a quarter, -2/4. Subtract a quarter, -3/4. Subtract a quarter, I'm back at -1. And now from -1, I'm going to 0, and so that means I'm going to be adding 1. And so from -1, I'm going to add a quarter, in which that gives me -3/4. -3/4, I'm going to add a quarter, -2/4. -2/4, I'm going to add a quarter, -1/4. And then from -1/4, I'm going to add a quarter and get back to 0. But we've gotten these points down. They're not complete just yet, because these are in terms of x squared comma y squared, like we said before. And so then what do we need to do to all of these values then? We need to square root them. Square root, square root, square root. And I think you get the gist of it. And we're going to keep doing that all around here, in which you may ask, okay, well, what about these negative square roots here? And what I have to say to that is that that's, maybe I can make another video following this up, making more sense of it, but it's almost just an exception in which you just have to carry out this negative out to the side over here. And so something like this negative, or this square root of negative 2 over fourths should really be treated as a negative square root of 2 over fourth. Like that. And then that should solve everything. I know it's not the best explanation, but I haven't found an intuitive way to think about that yet. Hopefully you guys can. If you can, like, you can leave it in the comments below. But once we do figure out all these square roots, then we'd be able to get our unit circle, in which then we'd be able to draw out over here our unit circle, in which now we have all of our values, 1, 0. This is a square root of 1/2. Yeah, this is 1/2, and now this would be square root of 3 over 2. This would be square root of 2 over 2, square root of 2 over 2, square root of 3 over 2, and 1/2. And then right here would be 0, 1. Went back around here. Now let's make sure we can see our other part of the unit circle, which now we have that negative in the square root there. We're just going to take it out, treat it as a regular negative. This is negative 1/2 square root of 3 over 2. Other point here, again with that negative, we're just going to take it out, which this is negative square root of 2 over 2 square root of 2 over 2. Other point here, this is going to be, again with that negative, square root of 3 over 2, 1/2. And then this last point here, negative 1, 0. We're going to keep continuing on here with, then now we would have a negative square root of 3 over 2, negative 1/2. And now at this point, what I'm really doing is you'd be able to use symmetry here and see that these 2 points, all that matters is just the, oh, I almost forgot the negative here. The only difference that matters is that they're reflected across the x-axis here. And all that would mean is that we'd be adding a negative onto the y value here. And so I wouldn't really need to calculate it from the unit circle to the left anymore. And so from like here to over here now, all I need to do is add on that negative onto the y value. Whoops, looking at the wrong one. Square root of 2 over 2, negative square root of 2 over 2. From right here as well. This value is negative 1/2 and negative square root of 3 over 2. And now this value right here, you can still do the same thing, treat this as the same thing, just adding that negative onto there. It would just be 0, negative 1 across here would be square root of 3 over 2 comma negative 1/2. over here would be square root of 2 over 2, negative square root of 2 over 2. And right over here would be 1/2 and negative square root of 3 over 2. And now with that, we can get rid of these arrows here. Now with that, the last thing we can do, if you so choose, is you can write down the angles here, in which this is 30, 45. You're always going 30, 45, and 60. If anything, if it makes it easier, you can first do jumps of 30, in which this is a jump of a third, and then you do another jump of a third here to 60. So 30, 60, and then of course 90. This would be 90. Do another jump of a third here, and going all the way around here would be 90, and then plus 30 now, so 120. Another jump of a third, in which now going all the way around here would be 150. Another jump of a third would be 180 around here, and you can keep going along with that. Actually, you know what? For sake of completion, let's just keep going. Doing another jump of a 30 around here would be 180 plus 30, 210. Another jump of a third here would be 210 plus 30, 240. Another jump of a third here, 240 plus 30, which would be 270. Jump of a third here would be 270 plus 30, 300. Another jump of a third here, 300 plus 30 is 330. Let me clear that up. 330, and another jump of a third, which would be another 30 degrees, would be 330 plus 30, which would be 360, and you have that whole 360 degrees in that unit circle. And that was a lot. But then there's one more in which you have to consider, in which you need to consider your quarters, in which that'd be your jumps by 45 degrees, which isn't too easy, but my bad, which is pretty easy. It isn't too hard. Because you know that these jumps across your axes are 90 degrees, and so you're pretty much just breaking those in half. In which, if you really want, you can break each of these 90-degree pieces by halves, and so this would be 45 degrees here, a jump here, 45, another 45 degrees, which would get us to 90 degrees, another 45-degree jump here, which would be to 90 plus 45, 135 degrees, another 45-degree jump, which would be 180 degrees here, another 45-degree jump here, which would be to 225 degrees, another 45-degree jump here, which would be to 270 degrees, another 45-degree jump, which would be to 315 degrees, and another 45-degree jump, which would be to your total 360 degrees of a circle. And so that's how you would label. Of course, you would overlap the third jumps of the 30, 60, 90, 120, along with the 45, 90, 135, alongside all that. But that can get really messy. I usually just like to draw your usual. This is 30. This is 45. This is 60. And then you'd be able to know by the jumps whether or not it's like what degree it is. Because something like, if you're trying to figure out this point right here, you'll be able to see, oh well, this is the first jump, like to the first point, if you were to start from 90, in which you can pretty much treat it as just a regular 30 degrees. But your starting point is at 90, so 30 plus 90 would be 120. And it can be the same exact thing, even for the negatives. So say if you're trying to figure out this point right here, you can say, okay, well, if I just set this as my starting, or like my 0, I would know that this is my first jump here, in which this is just regular 30 degrees. But where am I starting at? I'm starting at 180 degrees. So 180 plus 30 is 210. Be the same for anything else. I guess just one more example. If, say, I wanted to try to find this point right here, I can say I'm starting from right here, and now I can know, okay, well, this isn't the 30 degrees, this isn't the 45, this is the 60 degrees. So this is 60 degrees. This would be 60 degrees if my starting point wasn't right here. But my starting point right here, this is 270 degrees. Because, of course, you start from 0, you go 0, 90, 180, and 270. So now you have 270 plus 60. That's going to give us 330. So this is 330 degrees. Assuming that you're wrapping all the way from 0 across here. Because you may have cases in which you do start from 0 and you're just going negative. And if you're just going negative, you do the same exact thing, except you look at your starting point and you subtract that. Right? So if you really want to look at negative examples, we can. Let's say if you're trying to figure out this point over here, but you want to, like, say the positive and the negative angle. So in that case, what you can do here is, like, say, okay, I'm going to start right here. And I'm going to see, okay, well, I'm jumping from 1, 2 to the third point right here. Which in this case, it is 60, but it's a minus 60 because we're going the opposite way of the unit circle. Unit circle goes counterclockwise, right? That's positive. That's our positive. Negative goes clockwise, in which negative would go across this way. This direction right here is negative. And so this will be negative, but you're starting from here. But what is this starting point? Don't make the mistake of saying this is 270. This is not 270, because this is 270 if you start from 0 and go across here. But what is this? What is the starting point? The starting point, if you start from 0, go across here, then this would be negative 90. Negative 90 minus 60, this would be negative 150 degrees. Whoa, all right, okay, so there was a big jump there, and that's because I forgot something very important. When do we apply sine, cosine, and tangent to all this business right here, right? Because if we're able to get the angles of the unit circle onto these certain points with these x, y values, where does sine, cosine, tangent come in? So first off, I guess I'll just describe that for your basic trig functions, you're going to have sine, cosine, and tangent, in which you'll see this as sine of some angle theta. Cosine you'll see as cos of some angle theta. And tangent you'll see as tan of some angle theta. Just like that. And so if I give something like sine of 30 degrees, what exactly am I trying to get here? Because we know, okay, right here we have 30 degrees, but what do I get? Do I just return this whole point here? Or do I just return this value? Or do I just return this value? Do I return the x value, the y value, or some pair of them? And so the way I memorize this is, first off, is just by tangent. You're going to have to know that tangent of theta. Let me scoot this over here. Is equal to sine of theta over cosine of theta. This property right here is just something you're going to have to know. But as for the sines and cosines, the way I go about it is that for each of these points right here, you have an x and a y value. And if you're going in alphabetical order, x comes before y, right? You have x, y, z. And similarly, for these 2 points, you have 2 letters. You have an S and you have a C. Now putting them in alphabetical order here, we're going to have C comes before S in the alphabet. And so whenever I use cosine of some angle theta, I'm going to get its x value of that point. And when I use sine of some angle theta, I'm going to get its y value of that point. So sine of 30 degrees here would be this 30 degrees here, which means I'd be looking at this point. And I know that we have C and then S, and so that means I'd be getting the y value of this 30-degree angle at that point. And so I get square root of 3 over 2. As for cosine of 30 degrees, that's going to be 1/2. And this still works for all angles in which we were describing before. So something like sine of negative 90 degrees. What do you think that's going to be? Negative 90 is right here. This point right here, which is described by this pair, and sine comes after cosine, and so we get the y value. This is -1. We can even be fancy with this. We can say what is tangent of, let's go negative 150 degrees. Well, we don't really have tangent, but what we do have is our property over here. Tangent of theta, tangent of negative 150 degrees is equal to sine of negative 150 degrees divided by cosine of negative 150 degrees. And then keeping both of these in view right here, this is going to equal to the sine is our y value. So we're looking this point right here. And for our y value, we have -1/2 divided by cosine of negative 150. That is our x value, negative square root of 3 over 2. And which in total, if we simplify this, we're going to have a keep, change, and a flip. So this is, I guess just writing this out, -1/2 divided by negative square root of 3 over 2, which is equal to -1/2 times -2 over square root of 3. And you can see these 2's cancel out as well as our negatives here. And this together is going to give us 1 over square root of 3. Tangent of negative 150 degrees is 1 over square root of 3. And I guess just one more, for these tangents, if we're not working with any negatives, we can have something like tangent of, let's go 120 degrees. This is going to be sine over cosine. We still keep that same degree. And then now from the unit circle here, what do we have? Well, let's see, 120 degrees. Well, this is 180 degrees here. This is 90 degrees here. And so 120 degrees is somewhere in between here. And if I take a close look at this, well, if I start at 90, let's go 120 minus 90. That gives me 30 degrees. Okay, so starting from 90 degrees, I need to move 30 degrees counterclockwise, because that's the way the unit circle goes. And where does that bring me? It brings me to this first point over here. So altogether, this would be 120 degrees right here. And so I'm going to be looking at this point right here. And so we can get our values. Sine of 120 degrees, that's going to give us our y value, root 3 over 2. And then our x value is our cosine, which is negative 1/2. And then we do the same process as we just did before for our negative angle when we're using tangent, in which we're going to have keep, change, flip. We're dividing two fractions, in which you can already see where we're going to have the 2's cancel out here, and we're just going to be left with negative square root of 3 right over here. Making sure I did that right. Yep, should be good. And so tangent of 120 degrees is sine of 120 degrees divided by cosine of 120 degrees, and which gives us negative square root of 3 right over here. Hope that makes sense. But yeah, general, this is how I memorize the unit circle, and hopefully it works out for you guys. So best of luck with that, and thank you.